Hi everyone, and welcome to this virtual chemistry lesson, where I will go through the pH concept, neutralization reactions, and the autodissociation of water. These are all concepts that sort of interlink, they're all related to each other, and therefore it's imprudent to combine them all into one video, as to say. Um, At the start of the video, I will go through these concepts. I'd like you to take notes. I'd like you to pause the video where you need to, so you can follow at your own pace. And then at the end of the video, I will give you some examples of how to do calculations with pH and neutralization reactions. All right, so let's have at it. Before this, we've talked about acids in water solutions. And if you don't know that much about the general properties of acids and bases, I'd like you to look that up before you get deeper into this video. But those of you who are my students, you know that whenever you put acids in water solutions, they will react with the water. And this course will only deal with water solutions of various types. So when water and an acid come into contact with each other, the water will act as a base and accept a dissociated proton from the acid. For example, as the picture shows here to the right, we have a bottle of nitric acid. But a bottle of nitric acid containing a water solution of nitric acid is actually the following. It's a combination of oxonium ions and nitrate ions. And the reason for this is because the acid and water will have reacted with each other to form these as products. So this is actually a bottle of oxonium ions and nitrate ions, not a pure nitric acid solution, but in reality these ions are present in here. And you know that oxonium ions, they are what give acids their acidic properties or their corrosive properties as well. So the oxonium ions is what will actually act as an acid, so to speak. And the more we have, the stronger the acid will be. Let's look at bases as well. Whenever we put bases into contact with water, the water will act as an acid instead. In the previous example, it acted as a base. In this case, it acts as an acid. And it will donate one of its protons. The picture shows us a bottle of ammonia solution, where we mixed ammonia gas and water together. And this is then really the following. The ammonia will have reacted with the water molecules to form hydroxide ions and ammonium ions. And you know that the hydroxide ions, they give bases their typical base properties, and therefore also their corrosive properties. And not the ammonia itself, but actually the hydroxide, whenever we're dealing with water solutions. This is a simplification because the reaction of ammonia with water is actually a so-called equilibrium reaction. We haven't talked about those yet in this course, which is why we make this simplification, just to show what happens in a typical reaction with a base and water. Since ammonia is in reality not a strong base, it does not undergo complete dissociation. So for those of you who have studied more chemistry than my students currently have, you know what I'm talking about. If not, we will talk about this in a later video. So don't worry about that. So, but whenever we talk about bases, we cannot forgo the typical strong bases. The typical strong bases are hydroxide salts. They are salts with formed between a cation and the hydroxide ion of some sort. And since it's a salt, if we put it in water, we won't have a reaction, so to speak, but we will have the salt being dissolved in the water, and therefore the cations and anions will separate, forming large amounts of hydroxide ions. So by adding hydroxide salts that are soluble in water, and remember that there may be hydroxide salts, or actually I know that there are hydroxide salts that are not soluble in water, but if we have soluble salts, We put them in water and they are split apart into cations and anions. So by adding hydroxide salt, we directly add hydroxide ions, which means we can directly add base, so to speak. We get a very, very strong basic solution. Here we have an example. The picture to the right shows you pellets of potassium hydroxide, which is a solid salt. If we dissolve this in water, we can write this physical change as the following. Then we will, for every single unit of potassium hydroxide we dissolve, we will form a hydroxide ion. So by adding this, we directly add hydroxide ions. And this is what we have for the typical strong bases. They donate, or not donate, sorry. We directly add hydroxide ions into solution, pretty much. So, let's think a minute, let's pause and contemplate. We've seen an example where water and an acid react together, and we've seen an example where water and a base reacts together. So we've seen examples of water acting as both an acid and as a base. Is that possible? Yes, it is. In fact, the more of acid-base chemistry you get into, the more you will realize that a lot of substances can act both as acids and bases. But water is a typical example when you introduce this concept. Substances that can act as both acids and bases, they're called amphoteric or amphiprotic. They're the same thing, sort of, which means that they can both give away a proton and take up an additional proton. And this is interesting. Even if we have 100% pure water, that will be a mix of molecules that can act both as acids and bases. So, actually, some of the water molecules will react with other water molecules and form hydroxide ions and oxonium ions, as you can see here. Here we have a water molecule and another water molecule. They react to form a an oxonium ion and a hydroxide ion. And that is because one of them give away a proton to the other. And this process is called the autodissociation of water. This is something we need to know quite a bit about. In neutral water, the concentration of ions formed for both oxonium ions and hydroxide ions will be 1 times 10 raised to the power of -7 moles per cubic decimeters, or molar. It's the same thing. And this is something you need to sort of know. And once you get into the pH scale, this will be even easier for you to know and memorize. But in neutral water, we have these fixed concentrations of oxonium ions and hydroxide ions. And whenever I put square brackets around something like this is chemistry speech for the concentration of the thing inside the bracket. So adding brackets like this around the oxonium ion, we say the concentration of oxonium ions. And this is often used in formulas later on, for example, equilibrium expressions and such. So it's a good concept for us to start practicing already. You should note that what I've drawn here, this is a simplification. In reality, we will have an equilibrium expression here, which I will show you later. We'll get back to that after we talked about neutralization reactions. But before we do that, we're going to look at the pH concept, because it's time for us to do calculations on acids and bases, and we don't do that without pH. So, let's ask ourselves, if oxonium ions are responsible for the acidic properties of solutions, how much of these oxonium ions can we find in nature? Right? Various things we find in nature will have various degrees of acidity. So, and the reality of this is that this varies a lot in nature. Concentrations can vary by many factors of 10. And let's take a few examples here. The concentration we find in lemon juice, the solution within a lemon, is 1000 times more concentrated than the concentration we will have in black coffee. And it will even be 10 million times more concentrated than that of seawater. So you see that we have a difference in many factors of 10 here. So we need a scale that can effectively deal with several factors of 10. If we want a scale that provides a way for us to easily compare various the acidity of things we find in nature. Whenever we're dealing with several factors of 10, we usually use logarithmic scales in science with a base of 10 if they vary with several factors of 10. So the pH scale is actually a logarithmic scale with a base of 10, and we'll get into this. So what we're going to do now is that we're going to look at the concentrations of oxonium ions in a few solutions, and then we take the logarithm with a base of 10 of each. So the concentration of oxonium ions of lemon juice equals 0.01 molar. And remember that square brackets mean the concentration of. If we take the logarithm with a base of 10 of this value, we will get -2. You can easily do that on your calculator. The base of 10 is standard for the logarithmic function you use there. If we look at the concentration of coffee, we will have 0.00001 molar. If we take the logarithm with a base of 10 of this, we get -5. The concentration of oxonium ions in seawater is even lower. There's a lot of zeros there. I'm not going to state them all. If we take the logarithm with a base of 10 out of the concentration of oxonium ions in seawater, we get -8. So, even though most things we find in nature vary by many factors of 10, the standard is that we find concentrations lower than 1. So that means we will get a negative scales if we have only values below smaller than 1. So to reflect nature, we multiply all of these values that we have determined here with -1, just to get rid of the negative sign. And if we do that as well, then you have determined the pH of these solutions. You should note that when we work in laboratory settings, we usually have concentrations way higher than 1 molar. So, but the pH scale is something that's made to reflect acidity of things found in nature. So, if we combine what I've said into a formula, here's the formula for calculating pH based on the concentration of oxonium ions. pH equals the negative logarithm with a base of 10 out of the concentration of oxonium ions. If we do calculations of what we had here before, the concentration of oxonium ions of lemon juice was 0.01 molar. The pH is the negative logarithm with a base of 10 out of this value. So you take the negative logarithm out of 0.01, and then you will get the pH of 2. The concentration of oxonium ions in coffee, we determine pH the same way, and you will find that the pH is 5. Seawater, which has an even lower concentration, will, if we put those values in, result in a pH of 8. Now we determine the pH of these 3 different solutions. And the interesting part here is that the more concentrated this solution is, the higher concentrations of oxonium ions we have, the smaller the value of pH is, as you can see here. This is the highest concentration compared to the other, and it has the lowest value. So low value means high concentration of oxonium ion, which in turn means a high degree of acidity relative to the others, right? So then I'm going to ask you another question. The pH of blood, that is about 7.4. But what is the concentration of oxonium ions in blood? The formula I showed you on the previous slide, that gave you a way to determine pH based on the concentration of oxonium ions. In this case, it's the opposite. We have the pH and we want to find the concentration of oxonium ions. Then we use the following formula. The concentration of oxonium ions equals 10 raised to the power of minus pH. And if we do that, well, we take 10 raised to the power of minus pH, which in this case was 7.4. That's in the title of this slide. We do that, and then you get the following. Lots of zeros before 398 molar, right? But this is way too many decimal points for any scientific context. We have 0.00000000398 molar. That's going to take a lot of time to write, and it's easy to mix up one of these zeros as you go along. So what we do is we write this in scientific notation. Scientific notation is when you take a number multiplied with a power of 10. And actually, I'm going to go back a little bit. We'll get to that later. But the scientific notation is when we take values multiplied by a power of 10. The power of 10 then, that will include the number of decimal points we have in this case. If it's negative, if it's positive, then it's how many extra zeros we add after the value. Right, now you've learned how to go from pH to the concentration of oxonium ions and back again. Well done. So, the pH scale is a measure of the concentration of oxonium in solutions typically found in nature. You often see it like this. A scale ranging from 1 to 14. 1 corresponds to very acidic solutions and 14 corresponds to very basic solutions. So the lower the value, the more acidic, the greater the value, the more basic. Because this is a measure of how acidic things are. And if we have very acidic things, we will be very close to 0. And then we'll approach here as we decrease the number of decimal points. If we have solutions that have very, very low degrees of acidity, well, then we will have higher values of pH, so the further to the right we are on this scale, the more basic the solution is. However, in a laboratory setting, we quite often move beyond this scale. We will have values below 1, below 0, so we can have negative values of pH, and we can have values greater than 14. That's no issue, really. It's just a decently concentrated sodium hydroxide solution, for example. But the pH scale 1 to 14, as you may have heard before, that's related to what we have in nature. In the lab, we're often beyond this scale. So we can have negative values over here and values up to like 17 up here. So keep that in mind. But if the pH scale is a measure of acidity, we need a similar scale to determine how basic things are in nature. And how basic a solution will be is determined by the hydroxide ions. The more we have, the more basic it is. And this, if we look at this in nature, it sort of follows in tandem with pH, that it also varies by many different factors of 10. For example, things with low pH will have let's start over. Things in nature with high concentrations of oxonium ions will have low concentrations of hydroxide ions and vice versa. We can then do the same thing as we did with the pH scale, but with the base of hydroxide ions and the concentration of hydroxide ions. So here you have two additional formulas. POH, which you may not have heard before, is the negative logarithm with a base of 10 of the concentration of hydroxide ions. The larger this value is, the smaller POH will be. So it acts like this. It acts the same way as the pH scale. The higher the concentration, the lower the value of the negative logarithm. But it's also the opposite of the pH scale, because this is a measure of how basic things are, not acidity. If we want to go from POH to the concentration of hydroxide ions, we take 10 raised to the power minus POH. So here we have the pH scale, and we went through that the further to the left, or the smaller value we have, the more acidic it is, and the greater the value, the more basic it will be. Then the POH scale, you can see like this. It's often typically also written between 1 and 14. However, the smaller the value, the more hydroxide we have, so the more basic it is. So it's the opposite to the pH scale. And the greater the value of POH, the more acidic the solution will be. And these, how acidic and basic things are, these sort of go hand in hand. So there is some sort of relationship between this. But for now, keep in mind that one of the scales shows how acidic things are. The smaller the value, the more acidic. The other scale shows how basic things are. The smaller the value, the more basic it is. So, and this might be the difficult part, but I'll try to take it slow, and hopefully you will follow me here. We did look at the autodissociation of water, and that showed us that there are always oxonium and hydroxide present in water solutions. The more hydroxide we add to water solutions, the more oxonium we add to water solutions, the less hydroxide will remain. The reason for this is due to the fact that oxonium is an acid and hydroxide is a base. Acids react with bases to form water, like so. So oxonium will donate a proton to the base hydroxide, and we will form two water molecules again. So if we add extra oxonium to a water solution that contains hydroxide, it will neutralize part of the hydroxide present in the water solution to form water like this. This is called a neutralization reaction, where both the acid and the base, that is, the oxonium and the hydroxide, they're neutralized because they lose their acidic and basic properties. They form water molecules that are fairly unreactive. Whenever we combine acids and bases, we call the resulting reaction a neutralization reaction. Since we have acid solutions, they will contain oxonium, and base solutions will contain hydroxide. This is the reaction that will take place. But remember that we will also have the ions left from the original acid and base. For example, hydrochloric acid forms oxonium and a chloride ion. Then that ion will also combine. So when we talk about the products of a neutralization reaction, we usually talk about water, like here, and a salt, because these ions aren't formed on their own, they need a partner in their original solutions. So the neutralization reaction that we looked at, that's the opposite of the autodissociation of water. And therefore we often write it like this, with this double arrow in between. Because this reaction can occur, water reacts with water to form oxonium and hydroxide. But as I just showed you, the neutralization reaction is when oxonium and hydroxide react with each other to react back and form water. To show two reactions in one, we can do a double arrow like this, so the reaction can go from left to right and right to left. This is called an equilibrium expression, an equilibrium reaction, whenever we have a double-headed arrow like this. And I won't go into this into depth because that's actually part of the Chemistry 2 course here in Sweden. But in reality, it means that we have fixed amounts on both sides of the arrow at any given time. For example, we can have 99% of everything in the system on this side of the arrow, so 99% will be still reactants, and 1% can be products, for example. So we'll have way more of the stuff on the left-hand side than the stuff on the right-hand side. So we'll have fixed proportions. And in this case, for this expression, it's going to be much, much less than 1% on the right-hand side. very small amounts of oxonium and hydroxides are formed in neutral water. But even though it's very, very small amounts, they're still formed and they influence how water reacts to acids and bases. So we need to sort of know our autodissociation of water and our neutralization reactions. So, because we always have hydroxide and oxonium in water solutions, and we can influence this proportion by adding either acid or base, we can get the following expression. pH plus POH equals 14.00 at 25 degrees Celsius. Exactly why this is, that's something I go through in chemistry too, because you need some knowledge about equilibrium reactions as well. You need to how to write up equilibrium expressions and do calculations on them before we can prove this. For now, I want you to take my word for it, because you're supposed to be able to work with pH and POH, and if you know this relationship, you can always go from one to the other. So without deeper proof, this is an equation or a formula that you can still use, and that's what I want you to do. So use this to solve problems for now, and then if you like this and you want to know more, look it up. And if you take the Swedish Chemistry 2 course, or if you study the IB chemistry, you will have an explanation as to why this is. So memorize it for now. Actually, you will have it in your formula sheets when you, for example, write a test, but it's not that difficult to remember. So, we've talked about what pH means. The lower the pH, the higher the concentration of oxonium. We've talked about pOH. That's a degree of how basic solutions are, and the lower it is, the more basic they are. Therefore, the higher concentrations of hydroxide. We then talked about just autodissociation of water a little bit and neutralization reactions. And you've gotten 5 different formulas from me that I want you to use to solve various types of problems. So, remember that we always work in water solutions right now when we talk about acids and bases. So, we have a solution with a pH of 5. Here's the sample exercise. So, I'm going to go through 3 sample exercises for you, and then I want you to work with exercises on your own. So, here's the first one. You have a solution with pH 5. What is the concentration of oxonium ions? What is the pOH of the solution? And what is the concentration of hydroxide ions in the solution? So, and that's because of the autodissociation of water, we will always have both of these. But we have a few relationships that we can use to work with this. So, you know that the concentration of oxonium ions, that's 10 raised to the power of minus pH. In this case, pH was 5. So if we take 10 raised to the power of minus 5, we will get the concentration of oxonium in the specific solution. And here we have the explanation of scientific notation. A number multiplied with the power of 10. That's how we write in science to avoid large amounts of decimal points. For pOH then, well, you have another relationship, and that is the pH plus pOH equals 14. So a constant. Therefore, 14 minus pH will be pOH. So 14 minus 5 will be pOH. In this case, it will be 9. Calculating the concentration of hydroxide ions then. Well, if you know the pOH, you have this formula. The concentration of hydroxide ions equals 10 raised to the power of minus pOH. So that will be 10 raised to the power of minus 9.0. And if we write this as scientific notation, it's 1.0 times 10 raised to the power of minus 9 molar. A few different formulas, but fairly straightforward. You get numbers, you put them into the formulas. And even if we didn't have the way to solve this immediately, we could determine the pOH. And once we've done that, we can easily determine the concentration of hydroxide ions as well. So, let's increase the difficulty a little bit. You dissolve 5 grams of sodium hydroxide in 1 liter of distilled water. What is the pH of the resulting solution? If you'd like, you could pause the video here and try and solve this on your own. But I will go on and solve it for you. Well, you write a expression for what happens, which we've done here. The sodium hydroxide, it's solid when we start. We dissolve it in water, so we write an arrow with water above it. And then we have free ions in solution like this. Then we write down what we know. We know that the mass of the sodium hydroxide that we put in the water is 5. You know that the molar mass of sodium hydroxide, that's the molar mass of sodium plus oxygen plus hydrogen. Sum that up. That will be 40.00 using our periodic table. The decimal points may vary depending on the periodic table you use. Well, you know that the number of moles, or the amount, equals mass divided by molar mass, so we can easily determine that, which is in this case 0.125. In this expression, you have 1 to 1 to 1 molar ratios here. For every sodium hydroxide that reacts, or breaks up, dissociates as we say, even though it's not an acid or base in that sense, but whenever a salt splits up, we also call that dissociation. When it dissociates to free ions, we get sodium ions and hydroxide ions. And for every one of those that splits up, we get one of these and one of these. So the ratio here is 1 to 1 to 1. So, since this is how many, this is just a number, how many of sodium hydroxide units we have, we can then easily determine the number of sodium ions and hydroxide ions. Like so. You know that the volume in this example was 1. So the concentration of hydroxide ions, that's what we're interested in, is the number of moles divided by volume. So the amount divided by volume. So we know that the concentration of hydroxide ions in this solution is 0.125. So you have a formula here. You know that pOH is the negative logarithm out of the concentration of hydroxide ions. We have the concentration of hydroxide here. Hydroxide and concentration. Perfect. We put that into our formula and we get that the pOH of the solution is 0.90. Okay. You have another expression, and that is that pH equals 14 minus pOH. The sum of pH and pOH is 14. So, then you can determine pH quite easily by just taking 14 minus pOH. And then you will get that the pH is 13 dot or 0.10. And that is the answer to this sample exercise. The pH of the solution is 13.10. It has a low pOH value, which means it's basic. Or you can say that it has a very high pH value, which means that it's basic. All right, let's look at neutralization reactions then. In the lab, let's say that you mix the following two solutions. You mix a sodium hydroxide solution with a concentration of 1.0 molar. You take 50 milliliters of that and you mix it with 20 milliliters of a 2.5 molar hydrochloric acid solution. What is the pH of the final solution that you formed here? And remember, we need to think about what is the final volume after mixing. That's going to be 70 milliliters, right? So a few things to think about here. I like to do it like this. I'm going to go into depth for a rather easy exercise, but that's just to show you what actually sort of happens, right? My hope is that it will help your understanding of this process. So I like to do it like this. You determine what we have in each solution first before we mix them. In solution 1, well, you can write an expression for this. It's the same expression that we used previously. You write the formula for the physical change in this case. You then make a table with the relevant things. And you start putting in numbers. You know the volume. It's 50 milliliters. If we convert that to liters, because we need it in cubic decimeters, it's 5.0 times 10 raised to the power of minus 2. Pretty much take 50 divided with 1000, and then I've written it in the scientific notation here. You know that concentration is 1.0, and you know that the number of moles is 5.0 times 10 raised to the power of minus 2, because we have the following expression. Concentration multiplied by volume equals the number of moles. So it's going to be the same as we had up here, because something times 1. So we know the number of moles of sodium hydroxide. We also know the ratio. We talked about this in the previous sample. For every sodium hydroxide that breaks up, we get 1 sodium and 1 hydroxide. That means we can predict that if all of these break up, we will get the same number of hydroxide ions based on the ratios. So we know the number of moles of hydroxide ions in solution 1. Let's stop there. Then we look at solution 2. In solution 2, we have hydrochloric acid that will react with water to form, so this is a chemical change, to form oxonium ions and chloride ions. We write the formula, we balance it, then we make a table. We put relevant things into our table here. We know the volume. Scientific notation we write like this because we need to have it in liters. The concentration we have in the exercise, it's 2.5 up here. And for the concentration of volume to match, we need to have cubic decimeters into both. So that's why we changed the volume to the appropriate unit. Same again, we know that concentration multiplied by volume equals the number of moles. So if we do that, we will have 0.05, which if we write it in scientific notation is 5.0 times 10 raised to the power minus 2. In this case, we have a ratio of 1 to 1 to 1 to 1. So we can predict the number of oxonium ions formed, the number of moles of oxonium ions formed, which is 5.0 times 10 raised to the power minus 2. We could also predict the chloride ions in this example and the sodium ions in the previous one, but that's not what we need to solve the exercise. But feel free to put everything into this table if you want to. That's fine. So now we know exactly what's in the two solutions. We've determined the products formed in the two solutions. Now we can combine them and see what happens. So I've taken the products of the acid in water, it's oxonium and chloride, and we mix that with the products of when we dissolve the sodium hydroxide salt. And a reaction will take place, a neutralization reaction, and we will form water, like so. So let's look here a little bit. Well, first and foremost, you know the number of moles here. In our previous table, we found out that the number of moles of oxonium is 5.0 times 10 raised to the power minus 2. And the same goes for the hydroxide. Okay, these will react in a ratio of 1 to 1 to 1 to 1 to 1 here. And we will get the following number of moles of water formed. We could talk about how much sodium chloride is formed, but we're not interested in that, right? So we only use the boxes in the table that we actually need. Otherwise, it takes too much time. And this is the interesting bit for this specific example. We have just equivalent amounts of oxonium and hydroxide. So when all of these are used up, all of these are used up. So we will have nothing left. Therefore, they neutralize each other, and the oxonium ions we've added from the acid and the hydroxide ions we've added from the base, neither will affect the final pH because they cancel out. So we're left with neutral salt water, because you remember sodium chloride was formed as a product of this. And neutral water has the pH of 7. And that pH comes from the autoprotolysis of water, or the autodissociation of water, which we usually say. And that still takes place. Actually, I'm gonna change that immediately. Bear with me. There we go. Now it's correct. So the autodissociation of water which still take place, which you see here. So we'll still form amounts of hydroxide and oxonium, even though the acid and base that we mix here, those are cancelled out. We still have oxonium and hydroxide. So we have a neutral solution which corresponds to a pH of 7. So that's our answer. The pH is 7, and the volume in the solution is 70 milliliters. If we did not have equivalent amounts, say that we had way more hydrochloric acid than we had sodium hydroxide, then we would have needed to find out how much oxonium would remain after the reaction, number of moles, divide with the new total volume to get the concentration of added oxonium ions. Then based on that, we can determine the concentration and the pH of the final solution. But in this case, since they cancel out, we will just have neutral water, and you know that neutral water has pH of 7. Here you have an alternate solution to the same thing, because we've practiced before that whenever you mix an acid and a base, you will form water and a salt. So if you know that, and you know, or you can figure out which salt is formed, that's not always that easy for other type of exercises, which is why I went through a more complicated version of how to solve it. But if you know the salt, then you can simply write a balanced equation with where the acid and base solution react to form water and a salt, balance it, and then you do calculations as usual. So in this case, we could write the same thing that we've done using a few reactions. We can sum it up like this. If we figure out that it's chloride and sodium that will form the salt, then you know that water will also be there. You can balance this. It is. You make a table, and then you can solve it as usual, and then you figure out that neither of these will be left over. Both of these will be used up completely because we don't have a limiting reactant. And then you can determine that the pH will be 7 because we don't have any one of these left. So that's an alternate way to do it. All right, that's it. I've talked for a while now. Now I want you to work with exercises in the course compendium if you are my students. If you're not my students, it was fun to have you listening to this presentation. Good luck and have fun.